Hi, this is Jim Plank. This is the next video of doing network conversions. This one is going to convert a value that has been encoded by a time into its complement in any of the three encodings. So its complement in terms of time, spike train, or value. As always, if you stumbled on this by mistake, there is the main repo for this work. And there is an introductory markdown file in its README and a video that goes through it in detail. If you haven't watched that or read that, I recommend that you do so that you can understand the content in this video more effectively. Okay, we are in the repo for the GitHub repo. I just pulled it and now we're in the terminal on my Mac, and what we're going to do is we're going to go over the network that's in figure 10 of the paper. So, figure 10. Okay, now in this network, we are going to get a value encoded by a time. We're going to spike at that time step according to the value. We're also going to spike the S neuron at time step 0, and then it is going to convert it to its complement as a time, as a spike train, or as a value. Now the mechanics of this network are actually pretty unexciting, even though it's a bigger network. These four neurons are the exact same as in the last video, which was figure 4, basically converting a time to a value. Once we convert the time to a value, that value is actually in this neuron. Now we're just converting the value into its complements, which is a very natural thing by spiking into it, setting up a spiking neuron, spiking into it. When we spike in its complement, it reaches its threshold. That time neuron spiked, and then the spike train and the spike value are also attainable from this neuron. Again, this is basically just a composition of the other networks in this paper. However, we'll go through the mechanics of how it works using the software, which will take some screen jacking. So the main script here is script 6, time to complements. Takes the maximum value, which in all our examples we'll use 8, the value 3, open source framework. Okay, and now it's got a lot of stuff. And the reason is there's a column for each one of these neurons, and there's 7 neurons. So that's okay. Let's just resize our screen and make it huge. And now we can see everything. Okay, so we spiked the time value as a time here at time step 3. And then what we see is the complement of 3 when the maximum of 8 is 5. So the spike train complement is 5 spikes right here. The time, complement's time here is 14. So the reference time is going to be 9. So if we subtract 9 from the time step of this, we'll get the complement. Regardless, we'll show that for other values. And then the C value will have a value of 5 at the end, which is here. Okay. So that goes through the mechanics of that network. Let's go ahead and change the 3 to a 4. What do we expect? We expect, now the complement of 4 is 4, so we expect this spike train to have 4 spikes in it, starting at time step 11. The time spike will be 1 sooner, so that'll be at time step 13. And then this value here at the end will be 4 instead of 5. So everything true? Yep, spike train of 4. This is coming at time 13. That value is 4. Let's go ahead and try the maximum value. Maximum value is the minimum complement. That means this neuron should not spike at all. This neuron will spike at time 9. And this neuron here will have a value of 0, sitting in it at the end. Okay, so did we lie? Nope, no spikes. Time step 9, value of 0. Okay, flip it around. Let's go to value of 0. Now we should have a train of 8 spikes. This neuron here, we should spike it at time step 17. And then this neuron here will have a potential of 8 at the end. Okay, do we get it right? Yep, 17, 8 spikes, potential of 8. Okay, so even though it's a bigger network, it just works using all the principles from the other networks. This illustrates how it works. The network itself I'm not sure at this point we really need to do this for all the networks, but we may as well. Okay, so here we see all of the neurons with their names, and we see the various thresholds set, right? This one's thresholds n+1, that one's thresholds m. Those are there. Here are all the synapses, various weights and delays, all good. As is talked about in the paper, if you don't need the complement as a spike train, you can delete that neuron and everything's fine. If you don't need the values of potential, you can delete that neuron and everything is fine. Can't delete that neuron. And then you could adjust the timings according to that. Again, that is mentioned in the paper. Okay, nice and quick. See you for the next one.